Okay, so welcome to the advanced conduction lecture series, and this is up till now. Okay, I mean, for now, this is the last lecture. Okay, but that does not mean that I will not update this lecture series, because any subject we cannot say that it is complete. There are so many things that can be covered. Okay, so this playlist will be updated, okay, as and when I will feel. Okay. So, without any delay, let me start this. So, this is lecture 22. So, we have covered 22 lectures for conduction from basic to advanced. Okay. Now, here what we will do is we will see the exact solution of the semi infinite slab problem. Okay, and this solution is also termed as similarity solution. Okay, similarity solution. Okay, so I may have to take one more lecture. Okay, I mean, if the solution is not completed in this lecture, because I don't want to hurry and I don't want to miss anything. Okay, similarity solution. So let us first again just write the governing equations and the boundary conditions. So if I roughly draw, then this was our schematic of the problem. Okay, and where this was our x direction, so it was an one dimensional problem, right? So governing equation will be, now I don't have to explain, you can write it in your dreams also. Governing equation will be this thing, right? Okay, and what will be the boundary conditions? Okay, so let us write the boundary conditions. The exact problem was that at time t equal to 0, at t equal to 0, that is the start of observation, you have put a heater in this region so that you can maintain. Okay, so here at time t equal to 0, you have started to maintain temperature at x equal to 0 is equal to some T1. That means temperature at x equal to 0 for any time that is greater than 0 is equal to T1. You are maintaining that temperature by any means. Practically you can do it by putting a heater. Okay. Now boundary condition, that means mathematically we are writing it like T at x equal to 0 at any t greater than 0 is equal to T1, right? What else? This was the first boundary condition. The second boundary condition is T at x tends to infinity, okay, at any time t greater than 0 is equal to T ambient. Okay, and here I can write it as, okay, not T infinity, maybe T ambient. I mean, what did I take in the previous lecture as ambient temperature? Was it T infinity or TA? Just let me see, to maintain the continuity, it was T infinity. Okay, it should be T infinity. Now some of you might get confused that in the previous lecture I wrote this one, that is t at x equal to delta t comma t greater than 0 is equal to T infinity. So let me tell you, both of these are correct, both of this and this are correct. Then what is the thing? So I should have written t at x greater than equals to delta t. Now, now had there been an actual heat penetration depth, then I could have said that yes, this can be the boundary condition. But ideally, I mean, mathematically speaking, if you if you have a infinite slab, okay, then there is, I mean, that is the actual concept. That is the temperature will reach the ambient temperature at x equal to infinity. If you have studied the boundary layer theory, then you can make the analogy there, that is the boundary layer thickness a is an imaginary thickness. It is taken as the thickness at which we get the velocity is equal to 0.99 into u infinity, the free stream velocity. That means we cannot say that yes, this is the thickness at which the velocity is equal to free stream velocity. So the same thing is happening here. We cannot say that this is the finite distance from the start of the slab at which there is the ambient temperature existing. Okay, we cannot say that. Ideally and mathematically, it will reach to T infinity at x tends to infinity. Okay, that means I can also write this one. Okay, that is del T del x, x tending to infinity is equal to 0. Okay, these are the I mean accurate boundary conditions. And why this is not accurate? Because mathematically there exists no such finite heat penetration depth where we can get T equal to T infinity. So previously that was an approximate solution. Okay, that is why we we could put this type of boundary conditions. Okay, okay. But if somebody said that I am an engineer, then I need only some approximate distance at which, okay, the temperature is not equal to T infinity. If it is equal to 0.9 T infinity, I am happy enough. Then you can define something like that delta T. Okay, and we already have shown that that delta T will scale, okay, that delta will scale with root over of alpha into T, where alpha is the thermal diffusivity and T is the time instant at which you are observing. Okay, now these two boundary conditions are actually correlated. Okay, so here we will consider only this and this. Now let me write the initial conditions. Okay, initial condition will be T for all x. Now how can I write the for all x? It will be this one, and at T equal to 0 equal to T ambient. Okay, so this is the description, the mathematical description of our problem. Now let me do the okay, so here there exists a very important phenomena. So in the last lecture I asked you that can you find some transformation. Okay, so before that, okay, so before coming to that, can you non-dimensionalize this one? So I will be non-dimensionalizing this one. And what is the motivation behind non-dimensionalization? The primary motivation is to make the mathematical description simpler. Okay, so non-dimensionalization I will get. So firstly the governing equation. Okay, so let me define the non-dimensionalized variable first. So T is equal to, see, if I put T minus, if I put T minus T infinity, okay, then this will become 0. Then here I will get at this boundary condition, that is x tends to infinity, I will get this equal to 0. Now you can argue that if I take T minus T1, then I will get this boundary condition equal to 0. So you can try that also, but here I am taking T minus T infinity by T ref. But you can also try by taking T minus T1 by T ref. Okay, and you should try, you should explore these things. And I will write here my non-dimensionalized x, that is x bar maybe, that will be x by some x reference. Okay, and then I will write my non-dimensionalized time by tau will be t by some t reference. Okay, so now if I write the governing equation again, that will become, so I will not spend here much time in explaining the things because I have done those ample amount of for ample amount of times, and now this will be 1 by alpha del 2 theta del x bar 2. So here it will be multiplied by t ref, and here x ref square is equal to del theta by del tau. Here I will multiply t ref, here I will multiply small t ref. So I can cancel out this capital T refs. Okay, now from this one, now I will just take all the constants in one side, maybe like this. So alpha x reference square by small t ref. Okay, now I will just take this as equal to 1. That means I am getting some x reference, and x reference is equal to root over of alpha t reference. Can you see the thing that this is nothing but the order of the heat penetration depth. Okay, so if I take the x reference as my root over of alpha t reference, then I will get something for which I will get, I will get some governing, I will get some governing equation which is of this form. Okay, so here actually physically this is my heat penetration depth. Okay, and this is very much practical. If I was asking you that, okay, just from your intuition tell me some x reference, what can be the characteristic length for this problem? There should be the heat penetration depth, right? Okay, so this is my governing equation. Let me write it finally. Okay, and let me just box it. Fine. Now let me write the boundary conditions. So firstly I will have theta at x bar equal to 0 for tau greater than 0 is equal to 0, is equal to 0 or 1. Okay, is equal to neither 0 not 1. It will be what? T1 minus T infinity by T ref. Now to make this thing 1, I can choose T ref is equal to T1 minus T infinity. That means from now onwards I will tell that my theta is equal to T minus T infinity by T1 minus T infinity. Okay, so this was the motivation of taking theta like this. Now this boundary condition will be, that is for any x bar from 0 to infinity, if I take tau equal to 0, I will get here 1, or sorry 0. Okay, and this is equal to 1, right, because I have taken theta as this. But now again I am just telling you that the try by taking theta is equal to t minus t1 by t1 minus t infinity maybe, or I think you should take theta equals to t minus t1 by t infinity minus t1. Then A will get this as equal to 1 and this as equal to 0. So your homework will be to explore with this option, and uh, let me know your observation in the comment box. And finally, let me write the initial condition in the non-dimensionalized form. So theta, uh, sorry, this was the initial condition, right? Okay, so this was the initial condition, and the second boundary condition would be theta at x bar tending to infinity and for any tau greater than 0 is equal to, so okay, so this will also be 0. Now it is okay. I am very sorry for that. Okay, so now let me ask you the question. Can there be any linear transformation? So can there be any linear or non-linear? So I will explore here the linear transformations. So transformation such that the solution of original variable is equal to the transformed variable. So can there exist any such transformation? So let us see. So I will explore here a general transformation. Okay, a general transformation I will explore here. So let us say that theta prime is equal to C1 into theta, and tau prime is equal to C2 into theta, and what else is remaining? X bar prime is equal to C3 into x bar. So these are transformed variables. Okay, transformed variables. These. Okay, and similarly these are the original variables. So this one. Okay, now I am saying that can there exist any triplet C1 C2 C3 such that theta dash equal to theta? Now you will jump and you will say that okay, C1 equal to C2 equal to C3 equal to 1. Obviously, please don't tell this. Obviously, this is I mean I am not asking this one. Okay, so I am not asking this one. This is the obvious transformation or the identity transformation. So apart from identity transformation, so I think I should write this here. Okay, so apart from identity transformation. Okay, so let us see. Now if I apply these transformations, these ones, into the boundary conditions, governing equations and all the things, then what I will get? So let me first do one thing. I will compare both the things. Firstly, the original problem. Okay, and secondly the transformed problem. Okay, so the original problem is having the governing equation like this. Okay, now if I write the governing equation for the transformed problem, again I will not explain this, it is the same thing. So I have to multiply 1 by C1 here and 1, okay, so 1 by C3 square in the denominator. Okay, so ultimately it will become C3 square by C1 is equal to, okay, so are you understanding? Because this is here I am having theta dash is equal to theta by 1 by C1. That is why whenever I am writing here theta dash, I have to multiply 1 by C1. Okay, because you see theta is equal to theta dash by C1. Okay, so del theta is equal to del theta dash by C1. Okay, that is why. Similarly, here I am having x bar dash is equal to x bar by 1 by C3. That means here I have x bar 2 times. So I have to multiply 1 by C3 square in the denominator, and that will go in the numerator. So, and here I will be having this one by tau prime into again. So here it will be C2 by C1. Clear? Hi. অসুবিধা নেই তো? খেয়ে এসছিস তুই? হ্যাঁ হ্যাঁ হ্যাঁ, ভিডিও রেকর্ড করছি, অসুবিধা নেই তো? খেয়ে এসছিস? আমি খেয়ে এসছি অলরেডি। Okay, so here this C1 and C1 will be cancelled out. Okay, now let us see the boundary condition. So first boundary condition was theta at x bar equal to 0 for any tau t greater than 0 is equal to what, 1, and the second boundary condition was this tending to infinity and tau greater than 0 is equal to 0, and the initial condition was this for all x, and for all x I can write it like this, and for tau equal to 0 is equal to 0. Okay, so here I think I should change the color, okay, otherwise it will be confusing, right? Arey yaar, color, this one, okay, this one, okay, fine. So here I will have this boundary condition in transformed variables. This is equal to 0, tau dash greater than 0. Okay, now theta is equal to what? Theta dash by C1. So I will be having here C1, right? I mean, ideally this is equal to 1 because this is equal to theta and that is equal to 1. Okay, so I will take this C1 here. Okay, similarly theta dash x bar tending to infinity, x bar dash tending to infinity, tau dash greater than 0 is equal to 0 because C1 into 0 is equal to 0. Then theta dash x bar dash tending to, okay, this is equal to 0 is equal to 0. Now you see, if I had a finite domain, okay, like if I had here x bar equal to delta t, then I was having here x bar dash equal to C3 into delta. Okay, then if you will see, if these two conditions has to be satisfied, and which condition, that is theta is equal to theta dash. Okay, I will explain it later. Now this is the description of the original and transform problem. Now my question is, can I have any transformation such that theta is equal to theta dash? If I have to have this, then I will require the governing equations and the boundary conditions exactly same. If I am having it only if, okay, if and only if I am having all the boundary conditions and the governing equation same, then for every time I will get the same solution, theta equal to theta dash. Okay, so let us see that. Now if the governing equation has to be same, then from these two equations I will have C3 square equal to C2, right? And if this boundary condition has to satisfy, then I have to have C1 equal to 1. Okay, and there is no restriction in these two equations and these two equations, these are exactly same. Okay, but now you see that if I was having here x bar equal to some finite, that is delta, some finite thing, so here I would have x bar dash equal to C3 into delta. So if I have to have this boundary condition is equal to this boundary condition, then I must satisfy C3 equal to 1, and then from this equation I will be having C3 equal to C2 equal to 1. That means this transformation. So I have to find a transformation apart from the identity transformation. So that is possible, I mean that is not possible if I am having a finite domain. That is, if my here, if I was having x bar equal to delta, then that is my finite domain. If the domain is finite, then I can see that I cannot have any such transformation where it is apart from the identity transformation satisfying that theta is equal to theta dash. That is, the solution of the original variable is equal to the solution of the transformed variable. Okay. So this was a very important observation, that is, this type of transformations cannot exist for a finite domain. Okay. Okay. Now you can see that I will now explore a special transformation, special transformation. And what is special about this transformation? This transformation, here I will have C1 equal to 1. So I have to satisfy C3 square equal to C2. So I will take C3 equal to K and C2 equal to K square. Then I am having C3 square equal to C2. Okay. Clear. Or I could have taken C2 equal to root K and C3 C2 equal to K and C3 equal to root K. Okay, I can have any one of them. So let me work with this one, C1 equal to 1. So let me work with this one. So this and this, so this and this are essentially same. Okay, same transformation. Okay, I mean not exactly same, but the I mean the relations between C1, C2, C3 are same. Clear? Okay. So now if I am having this, then I can see that if I am having this kind of transformation, then I can say that is my theta, which is a function of x bar and tau, is equal to theta dash, which is a function of x bar dash and tau dash, where my x bar dash is not an arbitrary x bar dash, but it is C3 into x bar, and my tau dash is equal to tau into x2, right? Sorry, tau dash equal to tau into C2, right? Okay, so here I have made a silly mistake, but I think the concept is clear. This should be C2 into tau. Okay, not theta. Okay. So that means, so now see, if I am having a particular coordinate, so maybe a particular coordinate, and that is I am having x bar naught and tau naught. In x bar tau plane, I am having a particular coordinate this, and I measure my theta at this coordinate. Okay, that means that will be equal to the theta at this coordinate also. Okay, tau naught into C2. Okay, the moment I am writing that my theta dash is a function of x bar and tau, then I can say that, I mean, if I can write it as I can write this as also theta as a function of C3 into x bar and tau into x2, because C3 and C2 are nothing but constants, and my theta is the function of x2 and tau, not the theta dash. Okay, so now we can see that if my coordinates are changing like this, so here now I know that what are my C3 and C2. C3 is what? C3 is root k. So this is root k x naught, and C2 is what? C2 is k. So this will be k into tau naught. So you now can say that my theta at x bar naught tau naught is equal to, take k equal to 2. This will be root 2x naught comma 2 tau naught. Take k equal to 4. It will be 2x naught comma 4 tau naught. Take that equal to 5. So it will be root 5 x naught comma 5 tau naught, and so on. Okay, that means if I draw x tau plane, okay, so x tau plane, okay, that means there are some particular points, okay, this is maybe, okay, so let me draw the points clearly. This is x naught comma tau naught, okay, this is what, root 2 x naught comma 2 tau naught, maybe this is again 2x naught comma 4 tau naught, and so on. So these points are not drawn in scale. Okay, now if I join this line something like this, okay, then all these will have a same temperature theta. Okay, now I am asking you that can you find any function f of x comma tau, or x naught comma tau naught, x naught comma tau naught, can you find any function x naught comma tau naught, okay, any function of x naught comma tau naught other than theta, obviously other than theta, that is constant along this line, that is constant along this line, can you find something like that? Let us see. So at this point, okay, at this point my coordinate is x naught comma tau naught, and at this point my coordinate is root 2 x naught comma 2 tau naught. Okay, so if I calculate here my what, x naught by root, okay, so if I calculate here my x by root tau, so at this point it will be x naught comma root tau naught, at this point it will be the x by root tau. I should write here, can you find a function f which is a function of x comma tau? I mean that was also not wrong, but still, can you find a function of x comma tau other than theta, or x bar comma tau, I am sorry, other than theta, which is a constant along this line? So we can see that here at this point if I find x by root tau, it is coming as root 2 x naught by 2 tau, right? Okay, I mean this, all this should be x bar naught, right? Okay, all this should be x bar naught. These things I think you can forgive me, right? But you see, okay, so x bar by root tau, so I have to put a root here, that is equals to x bar by root tau naught. If I calculate it for this one, at this point also I will have x bar by root tau is equal to same this by the root tau naught. That means I am having a function f equal to x bar by root tau, that is equals to constant on the line theta equal to constant. Okay, so I am saying that on the x bar tau plane I am having both of this function constant, there is no restrictions, there is no restriction. Okay, both of these are constant. Okay, that means I can say, okay, so now there can be two things. Okay, there can be two things. So I can have x bar comma tau. I can have f like this. Okay, I can have f like this. So that will be this, and I can have a theta like this. Okay, I mean, you can argue that okay, on these two lines, my theta and f can have two different values. That is totally acceptable. I mean, both of them are constant on a same line. Okay, my theta is equal to constant, but I don't know the value of theta here on this line. Okay, but I know the value of f here on this line because I know the form of f, but I don't know the form of theta. That is why I cannot say that my theta is equal to f. Okay, but I can definitely say that my theta is a function of f, that my theta is a function of f. Okay, so on the xy plane, if both f and g are constant, okay, so then you can say that f is a function of g. I mean, that can be an argument. Okay, I know that this argument sounds very rough, but this is one argument, that as my f is equal to constant. Okay, now see, theta is a function of x bar comma tau. Okay, now as my x bar by tau is constant, then I can see my theta is also constant. Okay, then I can write this is equal to a single variable eta, that is equal to some constant a into x bar by tau, root tau. Okay, now you will ask that why some constant a? I mean, from where it has come? Because you see, if this is equal to constant, then some constant a into this will also be constant. So that is same. I mean, that will not put any effect, right? Okay, so this is actually called a similarity variable. Okay, this is called a similarity variable. Similarity variable. I will give one more interpretation, like, I mean, you can do the same exercise for the tx plane. Okay, so, or let me do it for the theta x bar plane only. So theta x bar. Okay, now my theta x bar can look like this. Okay, so at x bar equal to 0, theta is equal to 1, and at x bar tending to infinity, my theta goes to 0. It will look like this. Now this is maybe at tau equal to some tau 1, and at tau 2 I will have another graph like this. So this will be at tau equal to tau 2. Maybe at tau 3 I will have another graph like this, that tau equal to tau 3. Now if I plot here, okay, my theta versus eta, that is equal to a into x bar by root tau, then I will have a single graph like this. Okay, so all these graphs, if I take any point here, maybe I am taking here this point, okay, this point and this point and this point. So I will represent this point as with this color, this point with green color, and this point with this pink color. Okay, so then all those points will lie on a same graph. Okay, okay, now you can see for this point you will have what, maybe this is your maybe x bar 1, So your eta will be x bar 1 by root tau 1. For this point your eta will be some x bar 2, maybe this is your x bar 2, this will be x bar 2 by root tau 2. For this one you maybe will have some x bar 3, and for this point you will have eta will be equal to x bar 3 by root tau 3. So you will have three different eta, maybe this will be eta 1, eta 2, eta 3, okay, and three different theta, okay. So here also you will have three different theta. So these values of three different thetas will be same here also, okay, and the eta 1, eta 2, eta 3 will adjust them accordingly. Clear? So just 1 minute. Okay, there is no question. Okay, that is okay. So theta is a function of eta here. Sorry, someone has come actually. So theta is a function of eta. We can see we have got a variable eta, okay, of which theta is a sole function, okay. That means we have got a very good thing, that is theta is equal to theta of eta. This is very much useful, okay. So now you have to write the governing equation. We are almost done, okay. This was the main thing. ছবি এসছে নাকি? ওই সিভি নিয়ে নাকি? So governing equation. So now let us write the governing equation first. This will be equal to del theta del tau. তোর কি অসুবিধা হচ্ছে এখন? তুই চাইলে থাকতে পারিস, কোনো অসুবিধা নেই। Okay, okay, okay. So now let us see. We have to write this equation in terms of only theta and eta. How can we write this? This I will explain, don't worry. See, this will be equal to, from chain rule of derivative I can write d theta d eta. So why I have write d and not del? Because theta is the only, sole function of eta, and this will be del eta del tau, okay. Now that is equal to okay, so I will write here theta dash. So theta dash is equal to d theta d eta, okay. Now what is del eta del tau? You see here eta is equal to a into x bar by root over of this, right? So then what will be del eta del tau? That will be equal to a into x bar, okay, into minus half, this is minus of half, into what? Tau to the power minus 3 by 2, okay. So this will be a into x bar into minus half, okay, into okay, so I can write here this as root tau into tau, because 1 by 2 plus 1 equal to 3 by 2, right? And that will be equal to theta into a into x bar by root tau, right, by root tau, into minus 1 by 2 of tau. Clear? And can you see this one? Low battery, how this was having 33% battery. Oh, okay, so let me on the low power mode. What has happened? Okay, so let me do it quickly because my charge is almost. So can you recognize this one? This will be what? These are eta. So this will be this by 2 tau and 1 minus sign here. Okay, so we got our del theta del eta. And what will be our this thing? So this thing will be, so first let us find the first derivative. and that will be equal to again d theta d eta into del eta del x bar. This will be equal to theta dash into, from this you can see very clearly that my del eta del x bar will be a by root over of tau. Okay. Now this thing will be, this one is equal to, okay, so I will do it. It will be, what I can write this as del x bar into theta dash a by root tau, right. So a by root tau is a constant, I can take this out, and this I can write as my d theta dash d eta into del eta del x bar. So I will here have my theta double dash into a square by tau. Clear? Okay, I think that is fine. So now if I equate these two, that is I will have this is equal to this. Okay, so let me write that. So that will be theta double dash into a square by tau is equal to theta dash into a by root tau. Clear? Okay, so then I can cancel them out. So here if I cancel this and this, I will have here 1 root tau actually. Okay, so I will have here root tau, and I can cancel this and this power. Then I will have theta dash. So I am having here root tau is equal to theta. Okay, there is one minus. So here I will have one minus here and also one minus here. Now root tau is what? It is eta by ax naught. So I think I am making some mistake. Okay, so here there should be one x bar also. This x bar actually. Okay, this x bar. There should be one. No, there should not be any x bar. Let me just see once more. Okay, this is a square. So this is this one. Okay, I have to put this one, and this was not root tau but only tau. So I will not have these things. Here also it will be tau, here also it will be tau. I have just equated this one and this one. Clear? So I am doing these things. So then I will have what? So these things will cancelled out, and I will have theta dash plus theta double dash a is equal to 0. You see, a is just a constant. That means this is an ODE. Okay, this is a very interesting thing. We have converted a PDE into an ODE. So this is the main feature of a similarity transformation. So if for any problem the similarity transformation exists, then with that similarity variable, if you have chosen a correct similarity variable, then with the help of that similarity variable you will be able to convert the PDE into an ODE. Okay, that is what we have done here. Now let me write the boundary conditions. Boundary conditions will be theta dash at eta equal to 0. Okay, that means what? At the x bar equal to 0, and that I was having, this was equal to 1, and my, sorry, not theta dash, it was theta, not, and my this one tending to infinity is equal to 0. See, this is a second order derivative. Okay, I mean a second order ODE, sorry, a second order ODE. So I need only two boundary conditions. But here the initial condition is already embedded, because in this tau the theta is already embedded. So eta is what? Eta is my x bar by root tau, right? So if my tau is equal to 0, and that is my initial condition, that means this is going to infinity, and that was also equal to 0. That my initial condition was also equal to 0. So if I put the initial condition, then I will get theta at eta tending to infinity. Why eta is tending to infinity at initial condition? Because eta is x bar by, I mean a into x bar by root tau. That means if I put tau is tending to 0, that means eta is tending to infinity, and I know that my initial condition is saying that my theta is equal to 0. That means this condition is both expressing the second boundary condition and the initial conditions. Okay. Now let me quickly solve this ODE. So I can write this ODE as d theta dash d eta into a, okay, is equal to minus theta dash. Clear? So I can do this one. So 1 by a minus 1 by a d eta, right? That means I can write that my ln, this one, I mean if I do the integration correctly, it will be minus eta by a plus some, maybe here I will write my c dash, okay, because c1, c2, c3 I have already used. So my theta dash, and that is equal to d theta d eta is equal to some c double dash into e to the power minus eta by a. Clear? Where this c double dash is equal to e to the power c dash. Okay. Now I will have, if I do the integration for the second time, I will have something like this, e to the power minus eta by a d eta, right, plus some c triple dash. So this is my final solution, and here I need to find the c double dash and c triple dash. So let us see, and before that let me check if I have made any mistake. Okay, so here I think there should be one eta. Okay, if I have not made any mistake, no, as far as I remember. So let me check just one more the transformation. So this will be, this is correct, theta dash. Now let me check this one, a by, okay, ax bar is common, minus half this one, so I can write this as this one. So ax by root tau is equal to eta, so eta by 1 by 2 tau, that is correct. Okay, I think I have done a terrible mistake. Okay, so I have to equate this term with this term. This term I have written here like this, theta dash into a square by tau, theta dash into a square by tau, but this term is minus theta dash into eta by 2 tau. What I have written, oh my god, sorry, I am extremely sorry. Actually today I am a bit absent minded, and I am very sorry for that. Okay, so that means I will not have the equation like this. So the equation will be theta dash into eta plus theta double dash into a square equal to 0. Still it is an ODE, because it is only in terms of theta, that is the dependent variable, and eta, which is the independent variable, and the boundary conditions are okay. So now I will have this one, there will be a eta here, and there will be one eta here. Okay, then it will be eta square by 2a, it will also be eta square by 2a. Okay, it will also have eta square by 2a. Now it is okay. Okay, so this integral is essentially from 0 to eta. I mean, that is what you can do. Okay, so this is the answer. Now here these two are unknowns, this one and this one. Let us apply the boundary condition. So the first boundary condition is at eta is equal to 0. So from this integral what I can get at eta equal to 0, that is theta is equal to c triple dash, and that is equals to 1, right? Okay, that means my theta is equal to 0 to eta, okay, c double dash e to the power minus eta square by 2a d eta plus 1, and okay, that is okay. And see one thing, that I can just take this one and put it outside the integral because it is a constant, and just for, okay, correct, but this one is outside the integral. Okay, fine. Now let me put the second boundary condition, that is at eta tending to infinity, what I am having, theta is equal to c double prime 0 to infinity e to the power minus eta square by 2a d eta plus 1. Now let me work with this integral. I will take a transformation here, and that will be equal to, this will be equal to 1. Okay, now here before doing anything else, uh, can you see that if I take a equal to half, then I will have a simple solution. I mean, my eta square by 2a will be eta square. So just for the mathematical simplicity, you can a equal to, I mean, you can take a equal to 1 lakh, 2 lakh, 1 crore, e to the power 1 crore, anything, any constant. But just for the simplicity in the mathematical calculation, I am taking a is equal to half, and if I take a is equal to half, then I will have my theta is a function of eta, and that is my eta becomes 1 by 2 x bar by root tau. Clear? Just for simplicity. Okay, then this integral I will now calculate. So copy, paste. So here if I take a is equal to half, then I will have only this one, right? Okay, so now I take eta square is equal to z. Then, okay, battery is dying down very quickly, so I can have this one. That means my d eta is equal to half, okay, dz by eta, right? And eta is equal to what? Half dz, eta is equal to root z, right? Okay, I will substitute this one. This will be 0 to infinity, eta to the power minus z, z to the power minus half, okay, and 1 half is there, so this will be dz. Can you recognize this integral from your knowledge of engineering maths? This is half into, this is gamma of half, this is gamma function of half, and gamma half is root pi, so this is root pi by 2. Clear? That means this integral is equal to root pi by 2, and I have already taken my a equal to half. I have taken this. Okay, that means my theta, okay, at eta tending to infinity becomes c double dash into root pi by 2 plus 1, but from the boundary condition I know that is equal to 0. That means my c double dash is equal to minus 2 by root pi. So I have got both the things, both the constants. That means my theta, which is a function of eta, that is equal to half into x bar by root tau is equal to nothing but 1 minus, because this is, so here I was having 1, so there, I mean from this equation I am having 1, so 1 minus, okay, c double dash is equal to this 0 to infinity, okay, or 0 to eta actually, right, not 0 to infinity, 0 to eta, okay. Sorry, 0 to eta e to the power minus eta square d eta, right, because a is equal to half, okay, now it is fine, okay. So this is called as error function of eta, error function of eta, okay. And then I am having 1 minus error function of eta, and that is equal to, just let me see it once more. I think I have not made any mistake here. Eta is equal to this, right, okay. It is fine, okay, now it is fine. And see, this is error function of eta, and 1 minus error function of eta is called the complementary error function of eta, or ERFC, and eta is equal to our x bar by 2 into root over of tau, okay. And we have tables for error function and complementary error functions, okay. So this is what error function, and this is what complementary, okay, error function, clear, okay. So that means my solution of theta, that is a function of x bar comma tau, is equal to error function complementary ERFC, complementary error function of x bar by 2 into root tau, clear. This is the exact solution, okay. Now there are some important things. If you change the boundary condition, if you, I mean in the previous approach, in the approximate solution, I have done it both with the constant wall temperature, I mean if I put a heater that will maintain the temperature at x equal to 0, okay, for any t, I mean for any time that is greater than 0, and also I solved the same problem with the approximate approach with the boundary condition with a given flux that is maintained at x equal to 0 for any time t greater than 0. But for that, that is at x equal to 0, if I maintain the flux and not the temperature, for this boundary condition I cannot say at this moment that if some similarity solution will exist or not. I have to look for any similarity variable. If I can convert the PD from OD with that similarity variable, your task is to find the similarity variable. If you are able to convert the PD to an OD, then yes, you are successful. That means the similarity solution exists. So if the problem, you change the problem description by by little means, okay, by changing the boundary condition, that is I am just maintaining a constant flux, then I cannot say that my similarity solution will exist and my exact solution will exist. So unlike the previous approach where my approximate solution was working for both the boundary conditions, I cannot ensure here that, I cannot ensure here before checking that there will be exact solutions for both the boundary conditions, okay. So that was a caution. So with that I would like to end this lecture, okay. I hope that I could convey most of the things of the conduction which are required in M.Tech level, at least in M.Tech level. So there is something called another thing. I mean, there is something what I am talking. So if you can put an oscillating temperature at the, okay, so let me just put off, okay, no. So if you can put a boundary condition like this, that t, for any time t small t greater than 0, my t is equal to some t1 into sine omega t. So that is some oscillating temperature. For that also one exact solution exists. Okay, but the approach is a bit different. And in fluid mechanics we have the same problem. I mean, the governing equation and the boundary conditions will be exactly same. Only difference is in fluid mechanics you will have the independent variables as your one x coordinate, that is fine, and time, but your dependent variable will velocity and not the temperature for the problem of fluid mechanics, but the exactly same governing equation and the boundary condition. So after watching this video, if you have to solve that one, please don't think like it that okay, this is a fluid mechanics problem and this is a heat transfer problem. Okay, yes, these are two different problems from the practical point of view, but from the mathematical point of view they will have exactly same solution. So please build this kind of mentality. I mean, building this kind of mindset is more important than understanding these things. Then you will have to work, I mean, you will have to put very lesser amount of work. Okay, otherwise you will be like, okay, let me mark up the solution for heat transfer and let me mark up the solution for fluid mechanics, although both are same. Okay, so don't read the thing twice, understand the thing once and apply anywhere. Okay, so these philosophies are more important. Okay, so with this I will call it an official end for the advanced conduction series. But having said that, I can put more videos in future as and when I will feel it right. Okay, so I hope we will meet in some another video in advanced conduction itself, or maybe in any other lecture series. I have one lecture series in convection, and I am thinking that I will also bring one lecture series on radiation, okay, if I get time. So we will meet there, and you can put your suggestions, your doubts, or anything you want. Obviously that should be under my skills, my purview, then only I can help you. Okay, you can put those things in comment box, I will try to help you by my heart. Okay, and until we meet next time in any other video, I will